When you step onto a plane, it feels like magic. One moment you're on the tarmac, the next you're 35,000 feet above the clouds, sipping coffee and scrolling through your phone. But here's the thing, that magic is really just physics, engineering, and decades of trial and error working behind the scenes. Airplanes aren't just big buses that float. They're carefully designed flying machines that defy gravity while keeping hundreds of people alive, comfortable, and, mostly, happy. Let's pull back the curtain and see what really makes living in the sky possible. From wood and fabric to metal birds. The story of airplanes starts over a century ago, and it's a tale of curiosity, courage, and a touch of madness. In 1903, the Wright brothers, Orville and Wilbur, took off in Kitty Hawk with their fragile wood and fabric flyer. It barely traveled 120 feet before landing, but it marked the dawn of human flight. The aircraft wasn't comfortable, fast, or even particularly safe, but it worked. That was the point. Early planes were more like kites you could ride. Pilots had to be part engineer, part acrobat, part daredevil. There were no autopilots, no pressurized cabins, no Wi-Fi. Everything had to be improvised. Engines were tiny by today's standards, made mostly of cast iron, and often failed mid-flight. Landing on a field? Expect a few broken bones. Flying was a premium risk sport before it became a routine way to travel. As decades passed, technology improved, materials evolved, and aviation entered the metal age. Wood and fabric gave way to aluminum and steel. Planes grew bigger, engines more reliable, and flight distances longer. By the 1930s and 40s, transcontinental flights were becoming possible, and airlines started treating passengers with comfort in mind. Leather seats, white tablecloths, and silverware became the norm for the wealthy few who could afford tickets. Flying had gone from a daring experiment to a luxurious lifestyle. But here's the kicker. As the planes got bigger and faster, engineers had to think differently. Wood bends, fabric tears, and early engines overheat. Metal structures are heavier but stronger. Every pound mattered because the heavier the plane, the more lift you needed, and lift is not free. It's a delicate balance. More fuel adds weight, but less fuel limits range. Designing an airplane became a sophisticated dance between materials science, aerodynamics, and raw imagination. The jet engine arrived in the 1950s, and suddenly, flying wasn't just about bravery or luxury, it was about speed and efficiency. Jets could carry hundreds of passengers over oceans in a fraction of the time propeller planes took. Airlines started thinking about how to fill seats, keep passengers comfortable, and, of course, make money. From fragile wood and fabric flyer to multi-ton metal bird, airplanes had transformed, but the underlying principle remained: defy gravity without letting it win. Wings, the secret to staying up. If engines are the heart of a plane, wings are its soul. Without them, there is no flight. But how do wings actually work? The answer lies in a simple yet mind-boggling principle: lift. Lift is created because of the shape of a wing, curved on top, flatter underneath. Air moves faster over the top, slower beneath, and that pressure difference pushes the plane upward. Newton's laws, Bernoulli's principle, and a touch of magic combine to make you rise above the clouds. Next time you're on a plane, glance out at the wing. That gentle curve is holding hundreds of tons of metal, fuel, and humans against gravity. Incredible, right? Of course, wings don't just sit there. Flaps, ailerons, spoilers, and slats are all carefully calibrated parts that control lift, drag, and direction. When the plane takes off, flaps extend to increase lift at low speeds. Mid-flight, they retract to minimize drag and save fuel. Spoilers deploy to slow down during landing or turbulence. The wing is basically a multifunctional Swiss Army knife for flight. And yes, wings bend. When you see them flexing mid-air, it might look alarming, but it's perfectly normal. Engineers design them to absorb turbulence, redistribute stress, and prevent structural failure. The bending isn't weakness, it's resilience. Here's another fun fact. Wing design isn't just about physics, it's about economics too. Longer wingspan, better fuel efficiency, but fewer seats per gate at airports. Wider wings, more stability, but higher manufacturing costs. Every curve, every tilt, every winglet at the tip is a compromise between safety, efficiency, and profitability. Without wings, airplanes are nothing more than expensive metal coffins. With them, they become machines that can cross oceans, continents, and sometimes entirely change how humans interact with the world. Engines, more than just noise. If wings are the soul, engines are the heartbeat of a plane. They do the heavy lifting, literally, by turning fuel into thrust. But the process is both simple in principle and terrifyingly complex in execution. Most commercial jets use turbofan engines. Air is sucked in by a fan, compressed, mixed with fuel, ignited, and expelled at high speed. The result? Forward motion. Newton's third law. Push air backward, move forward. Voila, you're airborne. These engines aren't just strong, they're unbelievably precise. Temperatures inside a combustion chamber can reach over 1,600 degrees Celsius, almost 3 times the melting point of steel. And turbines spin at thousands of rotations per minute. Yet these machines operate reliably for thousands of hours with minimal maintenance. Modern engines are masterpieces of metallurgy, aerodynamics, and computer-aided design. Here's a fun perspective. A single engine of a Boeing 777 generates more thrust than an entire fleet of cars running at full power. And yet, despite all that power, airlines are obsessed with fuel efficiency. Every extra kilogram of weight burns more fuel, and every unnecessary pound of thrust wastes money. That's why airlines constantly invest in new engine designs, lighter materials, and better aerodynamics, sometimes saving millions of dollars per plane per year. Engines also affect how you experience flight. The roar during takeoff isn't just dramatic flair, it's physics and engineering in action. The hum at cruising altitude? That's a carefully managed balance of power, noise reduction, and vibration control, all designed to make your flight smooth and bearable. In short, engines are more than noisemakers or fuel burners. They're the beating heart that powers humans across the sky, turning an impossibility into routine. Pressurized cabins. Living above the clouds. Now let's talk about something you might take for granted. Air. At 35,000 feet, the atmosphere is a hostile place. Temperatures plummet to minus 50 degrees Celsius, oxygen is thin, and the air pressure is far lower than what humans are adapted to. Without pressurized cabins, you wouldn't last more than a few minutes. Cabins are essentially giant reinforced tubes pumped with air to simulate conditions closer to 6,000 to 8,000 feet above sea level. That's why your ears pop during takeoff and landing. The air pressure is changing, and your body is adjusting. It's also why planes need multiple redundant systems to monitor air quality, pressure, and oxygen levels. One failure, and the consequences can be catastrophic. Modern pressurized cabins are marvels of engineering. They filter air continuously, replace it every few minutes, and maintain humidity levels far higher than outside. It's one reason flights feel relatively comfortable despite being at extreme altitudes. And it's not just about survival. Cabin design balances comfort, safety, and efficiency. Even the overhead bins, tray tables, and seats contribute to how air moves inside the fuselage. Here's an interesting tidbit. Pressurization also limits how fast a plane can climb or descend. Rapid changes in pressure can stress the fuselage or harm passengers. That's why pilots carefully control ascent and descent rates. Another invisible layer of engineering keeping humans alive above the clouds. Navigation. Flying without roads. Unlike cars, airplanes can't just follow painted lines. There's no asphalt in the sky, no traffic lights, no stop signs. Yet somehow, hundreds of planes crisscross the globe every day without crashing into each other. How does that happen? The answer is a mix of technology, training, and a little human intuition. Modern aircraft rely on a combination of radar, GPS, radio signals, and sophisticated autopilot systems. Air traffic controllers act as invisible traffic cops, guiding planes safely along invisible highways thousands of feet above the Earth. Imagine flying from New York to London. That's roughly 3,500 miles over the ocean. You can't exactly pull over at a rest stop. Pilots follow designated flight paths, but they also need to react to real-time conditions, storm fronts, turbulence, or other aircraft. Even a tiny miscalculation could mean hours of delay, discomfort, or worse. Autopilot systems make life easier, but they aren't mindless robots. Pilots program routes, monitor engine performance, weather, and airspeed, and take manual control whenever needed. The cockpit is essentially a command center where split-second decisions matter. And the fact that thousands of flights reach their destinations every single day, that's nothing short of extraordinary. Flying without roads also means constantly adjusting to the invisible environment. Wind currents, jet streams, and pressure systems aren't always predictable. Pilots can't see them, but advanced weather systems and satellite data let them plan routes for efficiency and safety. Airplanes are navigating through a 3D maze that is constantly moving, and humans and machines together keep everything running smoothly. The tiny details you never notice. If you think a plane is just a tube with seats, think again. Every bolt, panel, and wire has a purpose, and countless invisible safety measures are built into every inch of the aircraft. Take de-icing, for instance. Before takeoff, planes are often sprayed with a heated glycol solution. It seems tedious, but ice on wings can be deadly. Even a thin layer changes how air flows over the wing, reducing lift and making the plane harder to control. That small squirt of liquid is literally life-saving. Even the cabin layout is meticulously planned. Weight distribution matters. Passengers, luggage, fuel, they all affect the center of gravity. Too much weight in the wrong spot? The plane might pitch forward or backward. Engineers simulate thousands of loading scenarios to make sure every flight is stable. Seats, tray tables, and overhead bins aren't just convenience features. They're structural components. A tray table lock isn't there just so your laptop doesn't slide. It's part of the plane's crashworthiness design. Overhead bins are tested to withstand dozens of pounds of force in case luggage shifts during turbulence. And let's not forget the invisible systems. Sensors that detect engine vibrations, fuel leaks, and cabin pressure fluctuations. Thousands of microchips and monitoring devices silently communicate with pilots and ground crews. Most passengers never notice these, but without them, flying would be much riskier. Even small comforts, like reading lights, air vents, and seat recline limits, are part of a finely tuned system. Airflow, temperature, and even noise levels are engineered to make life at 35,000 feet manageable. Airlines might advertise legroom and entertainment, but behind the scenes, it's all about physics, engineering, and psychology working together. Why flying feels like magic. By now you might be thinking, all this engineering sounds exhausting. Yet, when you board a plane, you don't think about lift equations, engine turbines, or air pressure. You just enjoy the ride. That's the real magic of aviation. It makes the impossible seem effortless. Flying feels smooth because airplanes are designed to isolate passengers from the harsh realities of the sky. Turbulence, absorbed by flexible wings. Noise, dampened by insulation and engine design. Temperature extremes, managed by pressurization and environmental control systems. Every inconvenience of life above the clouds is softened or hidden from you. Even the seating layout plays a role. Airlines intentionally create contrast. Economy is tighter, business is spacious, first is indulgent. Your brain notices the difference without thinking about why. That illusion of comfort and exclusivity is a carefully orchestrated experience. Then there's the soft product, everything outside the seat itself. Flight attendants greet you with a smile. Food is plated with care. Announcements are calm and measured. These subtle touches make you feel safe and cared for. Studies show passengers often rate the soft product, service, ambiance, small luxuries, higher than the hard product, the actual seat or plane model. In other words, flying feels magical not just because of engineering, but because of psychology. Even takeoff, that moment when the plane rockets down the runway, feels thrilling. Acceleration presses you into your seat, the engines roar, the ground falls away, and suddenly you're airborne. Millions of calculations, decades of engineering, and thousands of safety protocols are compressed into those 30 seconds. And all you feel is exhilaration. That's engineering disguised as an emotional experience. That's it for our deep dive into how airplanes really work. Which part fascinates you the most? Engines, wings, or the pressurized cabin? Have you ever wondered why your flight feels so smooth, or why every little detail inside the cabin is designed the way it is? Subscribe now to uncover more secrets behind the skies and see what really makes flights tick.